Hello everyone, let us continue our discussion. We are in week 7 and this is our third lecture. If you recall, we already derived the bending stress distribution over a section and we derived this expression sigma by y is equal to m by I is equal to E by R, right? Okay, so today our plan is to extend this and see how we can solve for a beam which is not having a standard section but built up section. But before that, let us take a quick example. Say we have a section of the beam given and then for this section, which is having width at the top as 2 centimeter and at the bottom it is 6 centimeter. The problem is the section is under sagging moment and the tensile bending stress is given as 300 kg per centimeter square. Right. Our objective is to find out sigma c from the given information. So what we do, we first find out the section properties, and for that we divide this section into known sections. So we divide it into 3 segments. So 1, 2 and 3. So you have a rectangular section at the middle and then 2 triangular sections on either side. Now if you look at the width at the top, so the base of the rectangular section is again 2 centimeter and then the base of the triangular section is obviously again 2 centimeter. Now for this cross section, let us first find out the location of the CG from the base. So let the CG be at Y from the base. So we can find out Y very easily. First, the cross section is A is equal to 2 into 10 plus half base, which is 2 times 10, and we have 2 triangular cross sections. So effectively we have 20 plus 20, so that means 40 centimeters. So our cross-sectional area is A equal to 40 centimeter square. Next we find out the location of CG, and for that we again consider the rectangular cross-section whose area is 20 and we take the moment of this at the base. So we have the distance of the CG of this rectangular cross section at 5 centimeter from the base plus half 2 into 10 into 1/3 of 10, where the CG of the triangular cross section lies from the base, times we have 2 such cross sections, so multiply it by 2 and then that is divided by 40. So effectively what we get, 100 plus we have 66.67 divided by 40. It is 4.17 centimeter. So y bar from the base is 4.17 centimeter, right? Okay. So now let us find out the moment of inertia. For that again, we'll consider first the rectangular cross section and then two triangular cross sections. But for moment of inertia, we have to start from the CG of the respective section and then we have to transfer it to the CG of the combined section. So if you start with rectangular cross section, we have 1 by 12 times width, which is 2, times depth 10, so BD cube. So that's the rectangular part, plus the area of this part, so 2 into 10 times the CG, which is at 5 from the base, minus 4.17 and square of this, okay, plus we have 2 times, because we have two triangular cross section. For each of them, we first find out the moment of inertia about their respective CG. So 1 by 36 times 2 times 10 cube plus area of each section. So half times 2 times 10, and then we have the CG, which is 1/3 from the base, 4.17 minus 10 by 3 whole square. Right. Okay. So if you calculate this, the first term is 166.67 plus, for the second part we have 13.78 plus 2, and then 1 by 36 BD cube. So we have 2000 divided by 36, and that is 55.56 plus we have 4.17 minus 3.33 square of that times 10. So it is 7.06. So effectively we have centimeter to the power 4 as the moment of inertia. So I is equal to centimeter with power 4. Right? Okay. So now we have the complete information and we can find out the bending stress distribution, and from there we will figure out the stress for the fibers under compression, right? Okay. So we have sagging moment. That means the top fiber is under compression and the bottom fiber is under tension, right? Okay. So this is the neutral axis, and then because we have sagging and tension at the bottom, so at the bottom we have, this is our sigma t, which is 300. Then if we linearly extend this, and we get the stress under compression. And we have this length, which is 4.17 centimeter. Therefore, sigma C divided by the total depth of the cross section is 10 minus 4.17 is equal to sigma T, which is 300, divided by 4. Right? So effectively we have sigma C divided by 5.83 is equal to 71.94. That means sigma C is equal to 5.83 times 71.94, and that is 419.42 kg. So now we can see how for a different cross section we can use the variation of stress along the cross section and figure out the stress at any particular location. Say for instance, if we want to find out what is the stress at this level, then we can find out from this linear distribution. And as we change this depth of the fiber from the neutral axis, we can actually find out the stress at different fiber when the beam is under bending, right? Now, not always we have a cross section like this with regular geometry. Sometimes we build up cross sections using different shapes and we use the combined section. So what happens when we have a built up section, right? So let us take a built up section and let this be a combination of two rectangular cross section. So we have two rectangular cross sections. One forms the flange at the top and one forms the web. Okay. Now the width at the top, say 20 centimeter. And the thickness of the flange is 10 centimeter. Thickness of the web is also 10 centimeter. And the depth of the web is again 20 centimeter. Now for this particular section, we apply a sagging bending moment, again a sagging bending moment of magnitude 4000 kg centimeter. We'll draw the stress diagram for this cross section. So for that, again, let us first find out the location of the CG from the base, right? So we have two different segments. The first one is the flange and second one is the web. So for that, again, we can find out the location of the CG from the base. So that will be A1 times 1 plus A2 times Y2 divided by A1 plus A2. And if we put the values of A1, so we have 20 times 10 times we have 20 plus half of the flange, that is 5, so it is 25, plus again for A2 we have 20 into 10, and the location of the CG for the second segment is at 10 centimeter from the base, divided by the area, which is 20 times 10 plus again 20 times 10. And then the CG is at 17.5 centimeter from the base. So it is here, and from the base this distance is 17.5. Now let us find out the moment of inertia I. For that, again first start with the first segment, and for that we have 1 by 12 b, which is 20 times d cube, plus area of this segment times we have this distance is 2.5, and then the CG is at 5, so altogether 7.5, so here 7.5 square, plus for the second one we have again 1 by 12 times width 10 times 20 cube, plus again the area of the cross section 20 times 10 times we have the CG of this is somewhere here, that is at 10, so effectively this distance is 7.5. So again we have 7.5 square. Now if you solve this, you get centimeter to the power. So now we have the moment of inertia I, which is centimeter to the power, right? Okay. Now we'll use the linear variation of the bending stress across the section, and then we'll find out the bending stress at the top and at the bottom that we will draw along the cross section, right? Okay. So the applied bending moment is 4000 kg centimeter. So M by I, which is equal to sigma, say, tension. Now the moment we find out tensile stress for sagging bending moment, it will be at the bottom, and then the Y for that is 17.5, right? Then what we get, sigma T is equal to 4000 times 17.5 divided by and this value is kg per centimeter. So if we plot this, at the bottom we have 3.6, and then the linear variation will give us sigma c at the top. So for sigma c, again we have 4000 times the distance of the extreme fiber from the neutral axis, and that is 12.5 divided by and this is kg per centimeter square. So here we have 2.6. As per our nomenclature, we have compression negative and tension positive. So that's the bending stress distribution over the cross section for this built-up section. So now if you have different built-up sections, you can easily find out the moment of inertia of the respective cross section and the location of the CG. And once you evaluate these two informations, you can apply the bending stress distribution model that we have developed, which is a linear distribution across the cross section. So as we move away from the neutral axis, bending stress increases, and we can plot the bending stress distribution over the entire cross section. Now you get the idea how you can use the model that we have developed, that is sigma by y is equal to m by I and is equal to E by R. Right. Now, not always we have beam cross sections made of a single material. For example, say we have a beam which is made of wood at the middle, and then on the either side it has steel cover. Right. So we have steel plate covering the sides of a wooden cross sections. Okay. Now the width of this wooden cross section, say B, and the width of steel is P. The depth of this cross section is, say, D. Now, when you make this cross section using wood and steel, we get a combined cross section, and for that again we have to find out the bending stress distribution. Let us see how we can solve this problem. Now, the assumption for this type of composite cross section, so assumption is there is no slip between the two different materials. Okay. That means when the cross section bends, the strain developed at this wooden fiber is exactly same what is developed in the steel fiber. Okay. Now, if that is the case, we can quantify that strain. So strain epsilon is equal to the stress in the wood fiber divided by Young's modulus of the wood is equal to the stress in the steel fiber divided by the Young's modulus of the steel. So effectively what we get, sigma S is equal to ES divided by EW times sigma W. And the ratio of Young's modulus of steel and wood is called the modular ratio M. It's a dimensionless quantity times sigma W. So what we effectively get is sigma S is equal to modular ratio times sigma W. And the modular ratio M, small m, is Young's modulus of steel divided by Young's modulus of wood. Now, the moment of resistance for this section, MR, is the moment of resistance offered by the wood, that is MW, plus moment of resistance offered by steel. So we can quantify the moment of resistance offered by wood, and if you recall, it is 1 by 6 B D square times sigma W, right? 1 by 6 BD square is the section modulus times the stress developed on the wooden fiber, plus we have 1/6 width of the steel cross section, that is T, times D square times sigma S is the moment of resistance of a single steel plate. So we have two steel plates, that is the reason we multiply this quantity by 2. Now we can further simplify this expression. So what we have here is 1 by 6 B D square sigma W plus 1 by 6 T D square. In place of sigma S, we can write M times sigma W times 2. Then if we simplify, we have 1 by 6, then D square sigma W we can take as the common factor, then within bracket we have B plus twice M times T. This means we convert the composite section to an equivalent wood section. So this is the equivalent wood section, and using the stress developed on the extreme fiber of the wood, we can actually quantify the moment of resistance of the. This way we can actually convert the steel part into equivalent wood, or also we can convert wood part into equivalent steel. In that case, we have to express sigma W as EW divided by ES times sigma S. And then we will find out the moment of resistance of the section in terms of sigma S instead of sigma W, what we have done here. Then we will get the equivalent steel cross section for this composite cross section, right? Now let us put some number. So if we have the allowable stress in the wood fiber, that is sigma W, as 70 kg per centimeter square. So sigma W is equal to 70 kg per centimeter square, and then let T, the thickness of the steel plate, is 10 millimeter, and B, that is the thickness of the wooden part, is 20 centimeter, and the depth D is 40 centimeter. Let us find out the moment of resistance of this cross section, and then we will also draw the bending stress distribution. Okay. So if we convert the section into equivalent wood cross section, so B equivalent will be B plus twice M, and let the modular ratio be 20, right? So what we have, B is 20 plus 2 times 20 times T, which is 10 millimeters. So that is 0. So we have 24 centimeter as the effective wood cross section. So we convert the steel into wood and we get the effective cross section when we convert it into equivalent wood cross sections. Okay. Now we can evaluate the moment of resistance MR, so which is 1/6, then 24, that is the equivalent width, times the depth of the cross section, D is 40, so 40 square, times sigma W, which is 70, right? Okay. Now, if you evaluate this, you'll get kg centimeter as the moment of resistance of the combined section. We can also find out the contribution from the wood, and if we do that, again, we have 1/6 times B is 20 times the depth is 40 square times 70. So this is equal to kg centimeter, and moment of resistance of the steel part is 1/6. Thickness is 0.1, that is the width of the steel part, then again 40 square times the sigma S, which is 20 times sigma W, that is 70. Now this is kg centimeter. We actually have a factor 2 here because we have 2 steel plates, and for both of them the combined moment of resistance is 74.67. So if we add these two, we get the total moment of resistance of the cross section. Now if we draw the diagram of the stress distribution, so for wood we have 70, so this is for wood. Similarly, we can also draw the same for the steel, and for steel it is 20 times 70. So it is 1400. So that is steel. Okay. So we get the idea of modular ratio when we have two different cross sections, right? Now you can have many other materials and you can build up different types of cross sections. Now in this example, we have two steel plates which are on the either side of the wooden central part. We can also have steel cover at the top and bottom. So let us say we have this wooden beam and then we have steel plate at the top and at the bottom. So this is the steel plate, and for both of them the width is now B. Central part has a depth say D, and the thickness of the steel cover is say T. And again, for sigma W, the stress is 70 kg per centimeter square. Modular ratio M is 20. Let us put the values of B, D and T. So B is 20 centimeter. Then D is 40 centimeter. And the thickness of the steel plate is 1 centimeter. Right? Again, it's a symmetric cross section. So we'll have neutral axis at the middle. And then we can draw a stress block for wooden part. Say this is positive and negative. So we have for wooden part 70 and 70. Then for the steel part, we have again linear variation of stress, but because we have only the top and bottom cover, so effectively this part of the stress diagram will be effective for steel plates, right? Okay. Now, again for this problem, sigma S is M times sigma W, so 20 times 70, so which is 1400 kg per centimeter square. Okay, so at this level we have the stress is 1400 kg per centimeter square. Now, if sigma T is at the extreme fiber, so sigma T is equal to 1400 divided by 20 into 20 plus 1, right? So this is 1470 kg per centimeter square. So the extreme fiber of the steel plate will have a stress 1470 kg per centimeter. Now, our objective is to find out the moment of resistance of the cross section. So again, we start with the central part made of wood, and for that we have 1/6 B, which is 20 times D, which is 40 BD square times sigma W, which is 70. And this again is 373.33 kg centimeter. For steel part, we have 1/6, then B is 20 times, we first consider the complete section and then we'll subtract the central part. Okay, so for that the depth is 42, so 42 square times 1470 minus 1/6 of 20 times 40 square times 1400. Now, if you solve this, you'll get 11 76.93 kg centimeter. So the total moment of resistance Mr is the summation of Mw and Ms, and the total moment of resistance we get 1550.26. So now you see, if we have a beam made of two different materials, then for that again we can apply the same bending stress distribution model, and we can find out the total moment of resistance for that particular cross section, which is contributed by the individual material. So for individual material, we find out the moment of resistance and then sum them up depending upon the type of geometry we have. As in this case, we have steel cover at the top and bottom, and in the previous case we had on the either side. Accordingly, we find out the moment of resistance of the section, and you can make different combinations, and for the different combinations you can find out the distribution of stress along the cross sections and also the moment of resistance. As you progress in your design course, you'll see you'll use this concept to design beams made of different materials, or sometimes using built-up sections also you develop beam model, and for that also you can find out the stresses at the extreme fibers, and accordingly you can design the beam. Okay, so with that, let us close here. This is the end of this week, and in the next week we will continue our discussion and we'll see how we can extend this for again the same beam cross sections, but we'll consider the shear force and how the shear stress is distributed over the cross section. That we'll take up in the next week. Thank you very much.